Cool. Well, welcome to this talk about Badgelife 101. It might be a little bit of a speed run because this is cut down from a 2-hour workshop I've done before, but hopefully it will still be good. There's a link there if you are interested. All the slides and all the resources are there, so don't worry about like trying to copy individual resource notes, and that link will be at the end as well. Quick bit about me. I call myself a hacker and a maker. I'm currently a Red Team tech lead for Google's Red Team. Mostly self-taught in electronics, so I'm not an EE, which I hope means that if I can figure out how to do this stuff, everyone else here can also figure out how to do this stuff, because I did not go through 4 years of education. I am on Mastodon. Technically, I still have an account on X or Twitter or whatever it's being called, but if you send me a DM there, there's a good chance I will never see it. Nothing I'm about to talk about is on behalf of my employer. I am here technically on vacation. This is how I spend my vacations, in case anyone's wondering. The speaker before me said that all presentations needed a quote, so I had to find one real quick. I thought about doing Sun Tzu, because that's what hackers do, but I decided to go with something a little bit more near and dear to my heart, and went with Hack the Planet, Dade Murphy. Unironically, Hackers is my favorite guilty pleasure movie. So what is Badgelife? If you've ever been to one of the bigger HackerCons, you've probably seen Badgelife in some form or another. It's electronic wearable badges. And it started off with some conferences were like, hey, it'd be cool if we did like electronics as badges. But then it started turning into people doing unofficial badges, people doing this as a form of expression, as a form of indicating that they're a member of a group, maybe your local DEF CON group or your local hacker space or something like that. Sometimes admission to special events at it. If anyone goes to DEF CON, you might be familiar with DC Furs, and they have some really, really cool badges, and it's also admission to their parties. There's a great documentary on Hackaday about Badgelife culture and how this all came to be as a way of showing off like interesting things we can do. Just to show that I have done some Badgelife, I'm not the best artist, so the artwork on them sometimes leaves something to be desired, but I hope the electronics makes up for it. I've been involved with about 5 unofficial badges. They've done various things. The one in the upper right, you could control what's displayed on those 14-segment displays via Bluetooth, which was an interesting challenge to make work. Some of the other ones were way brighter than intended. The one in the bottom we call the arc reactor because you could put it under your shirt and it would still be plainly visible to everyone else. Fun fact, I've also used these same skills to make electronic ornaments for friends and family for the holidays, which I think is a really cool thing to do. So, you know, my wife does paper crafting, and when I'm doing arts and crafts, it involves soldering irons and fiberglass and ordering hundreds of dollars of components from DigiKey. That's totally normal arts and crafts, right? I also have made a name badge that I wear at a lot of conferences. I forgot to bring it with me. As Ron mentioned, I did come here via a week in Europe, so I'm on kind of a round-the-world tour here. Quick expectations. When you walk out of here, I'm not going to have told you absolutely everything you need to know in order to make your own badge, but hopefully I will have pointed you to the resources that will allow you to fill in those gaps. But I will give you the overview of the process and show you what the things you don't know are, hopefully. And I'll have links for it. Please don't think that you can attend 45 minutes on this and then start touching what is called mains voltage, the electricity coming out of the wall. It will kill you, and it will hurt while it kills you. Some quick terminology. Badge, hopefully you figured out what that is if you're not familiar with electronic conference badges. There's a term that's used with a lot of them called SAO, which was a way to expand badges. They're add-ons of low quality. PCBs, I probably have used that term a couple times without defining it. It's printed circuit board. That's actually the thing that holds all the components together. MCU is another way of saying microcontroller, and we'll talk more about those. IC, integrated circuit, so if you don't have an electronics background, those are the fancy chips that do a bunch of things inside one chip. And then a UART is a nice way of saying an embedded serial port. So these are some terms that you might come across in various documentation, and that I will probably use again without redefining, so hopefully you will remember these definitions. So this is a rough idea of the steps that are involved in putting together a badge. You need a concept. You'll turn it into a schematic, then you'll take that schematic, you'll put it on a breadboard, you'll realize nothing works, and you'll go back to the previous step. Eventually, you'll get something that works. You'll write some firmware. If you've got a microcontroller, you'll do layout. You'll send it off to have a PCB made. While the PCB is being made and shipped to you, you'll realize that you screwed something up and need to fix it. So you'll jump back to the schematic and do that. But eventually, you'll end up with a product at the end that you can flash some firmware onto and will hopefully look nice. There are actually many other opportunities to go back to the beginning and start all over again, but those are the most common ones where the arrows are pointing backwards. If you're really lucky, you won't take any of those paths. No one I know who's done Badgelife has been really lucky. So how do you come up with a concept? Well, it turns out there's a lot of different things that you can do here, and it depends on what your goal is, right? Like I said, sometimes this is just a way of expressing yourself. You're like, oh, I want to do artwork, and I want to do it in an electronic format because that's what I'm into. I'm into electronics. I'm into all of this stuff. But sometimes you'll be like, I want everyone from my local hackerspace to know who each other are at a big conference because there's 20,000 people at it. Obviously not the long con, but at a bigger conference, and you want to know everyone who's there and be able to identify other members at a distance and things like that. Or maybe your whole CTF team wants badges, or maybe you want to do something for villages at conferences that have the village concept where there's small subsets. You can use it, you can sell them, and maybe make some profit if you do it correctly and figure out your costs. You can also do things that are interactive with each other, which I really love. Some DEF CON badges have had these components that would interact with each other, where you'd either physically connect them, or in some cases they used like short-range RF or infrared for badges to communicate with each other. And so you can have games that do that. One of the badges that I showed earlier I actually did for a work event, and we had a thing where if you met people from different teams at this recruiting event, attendees, as you did that, it would fill up the circles on the badge with the different colors from the different teams that you met. And so we did that as a way to incentivize attendees to go around and meet people who are working on different things, working on product security, working on red teaming, working on incident response. And so you could do something like that in terms of interaction function. So you'll run into some hard limits. I'm going to call these constraints. Some of those hard limits, you'll have two kinds of budget. Well, three kinds of budget, actually. You'll have your dollars budget, and that's probably, for a lot of people, going to be one of the bigger limiting factors. And there's two things you have to know to that. There's something called the bill of materials cost, which is all the costs that go into one individual unit that you're making, right? So that's the bill of materials is everything that goes into a single unit. That's your bill of materials cost. But it turns out there's other costs involved too. If you've never done this before, you're going to need some tools, and those have a cost associated with them. But beyond that, every time you send a new design to a fabricator, they usually charge you a setup fee because they have to do some work to make their machines produce the thing that you want produced, and they'll charge you a setup fee for that. And so that often is a flat fee on top of your order size. So if you're ordering 1,000 badges, that setup fee is not too bad. If you want 10 of them, that setup fee is going to be a pretty significant portion of your cost. Beyond that, you'll also have a time budget. And everyone, I think, probably has some idea of how this works for any project that you start, which is you estimate how long it's going to take, and then it ends up taking twice that long, and you end up with half as much done as you thought you were going to at the beginning. I guarantee you, if you're going to try to do Badgelife, it will take you longer than you expect. Even if you go, I've never tried this before, and it's going to take me a ton of time, it's going to take you 2 tons of time. And the other problem is manufacturing takes time. Things are better now, but if you'd asked me about this like 3 years ago during the height of the COVID pandemic, I would have said manufacturing takes an unknown amount of time because there were a lot of supply chain issues. And finally, power budget. So probably you figured out that these things are battery powered, and you can't just do unlimited things with electronics and batteries. Particularly when people will be wearing them, you also probably want to think about how much heat you're converting battery into. So you'll have some sort of power budget, but usually that's not super limiting unless you want to do something from like a coin cell or something. And we'll talk about your options for powering in a moment. You also have some considerations. These are a little bit different from constraints because these can be kind of flexible one way or the other. They are wearables. You need a way to attach them to something like a lanyard or a pin or something like that. Also, when you do your outline, don't put sharp corners on it. That's one I've learned from experience. It is painful. Through-hole component pins on the backside are also sharp and painful. Size and weight, again, it's a wearable. I did one that took 4 AA batteries once. That was a terrible, terrible mistake. Try wearing that for 4 days in the Las Vegas heat. The batteries will be the heaviest part of whatever you build. Also, overreaching. You may have this great idea. You may be like, I'm going to build something with an e-ink display, and it's going to scan for Wi-Fi networks, and then send it off to an AI coprocessor, and crack the Wi-Fi passphrase and all of this, which sounds like a really cool idea, and I would love to build something like that. But if you're trying to do it by yourself, I can already tell you, you're not going to do that in like 1 year. Sorry, there's a lot of engineering that's going to go into that. So if you want to try this, I suggest starting small. And finally, hardware supply chains. Again, COVID really screwed up the hardware supply chain. It is still, in 2023, somewhat screwed up. It's better now, but for a while, you could not buy the microcontroller that was used in Arduinos. You could buy a few of them at a time on eBay for really high prices, and they kind of looked like they'd been desoldered from other things, so it's not even sure that they were actually working components. But you couldn't buy them through the normal supply chain at all. You'd go to DigiKey, which is a big distributor of components, and you'd go on there, and they would tell you that it's a 104-week backlog. But if you actually contact them, they'll tell you that their system only goes to 104 weeks, and they have no idea when they're actually getting them. So don't depend on it. Like, some things are easy to find, like LEDs, resistors. Oh, that one is out of stock. I'll use a different one. But if you design around a particular microcontroller and you can't get it when you actually go to production, you're basically starting over again. So power options, right? Again, they're battery powered. There's a few different ways you can go about running things. You can use a coin cell, which is pretty cool because you generally don't need to regulate things out of it. It's very low risk. They're very cheap, easily obtained, don't weigh a lot. There's a lot of good things about them. Downside is they can't actually deliver that much power, right? Like, they're used for watches and things like that. So if you want to have like a whole bunch of LEDs and make it super bright, one of two things is going to happen. You're either going to need them to be really dim LEDs, which could be fine, you don't want to blind people, or it's going to just last a very short period of time as you drain that battery very quickly. Alkaline batteries are great too. They're cheap, plentiful, easy to replace, but they have the downside of, like, they're actually pretty heavy for how much power they store compared to other options. They're a technology that's been around for, at this point, in excess of 100 years, so they are not exactly the latest and greatest. LiPo pouch cells are popular. I get a little bit nervous with those. If you haven't ever done this, go on YouTube and search for punctured lithium-ion battery. It is a quite energetic experience. And the idea of putting that on the back of a circuit board and then having that up against my chest makes me a little bit nervous. So I would recommend, if you were to go with those, either get ones that come in a case that protects them, or I've seen some people 3D print a thing that goes over the battery on the back so that they're a little bit less likely to get damaged from being a wearable. And then you can also use some specialty batteries. I once used a battery called an A123. Has anyone ever seen one of those? We probably have some photographers in here if you've seen those. Some digital SLRs use those. They're great. They're 3 volts like the coin cell, but they actually have a capacity that will run something for more than about 15 minutes. So the downside to it is you have to order them, and you can't like field replace them super easily because, generally speaking, they're not going to be at like the drugstore. Some tools that you might want to have. We'll talk a little bit about the electronic design side of things. It's called EDA. Electronic Design Automation is the suite of tools that takes you from a concept all the way through sending off a design to be manufactured for production. On the EDA side, there's a bunch of different tools out there. I like KiCad. It's free. It's open source. It's become quite mature at this point. If you're not trying to design like computer motherboards, it's capable of doing just about anything shy of those high-speed traces. Eagle used to be very popular because they used to have a free version that was quite suitable for things. You can now get like the free version from Autodesk, but based on Autodesk's history, I would not expect that to exist much longer. They want to push everyone into subscription models, and even the education subscription for Autodesk is like $300 a year. So if you're making like one badge, that seems like a really poor return on investment. That being said, if you are made of money, you can buy Altium, which is basically the industry standard for making things like motherboards and The boards in laptops and displays and things like that. Super high end will do absolutely everything for you. I think they've even found some way to put like Chat GPT into it at this point so that you can just be like, make me a circuit, and it does. That being said, it's like thousands and thousands of dollars a year. If you're a reverse engineer, it's the IDA Pro with all the decompilers of the EDA world. And then there's Easy EDA. It's web-based. It's very limited in its capabilities, but it's free. It's from one of the companies that makes circuit boards. If you just want to check out what this whole thing is about, though, you can just go there and start doing it in your browser, which is pretty cool, and you don't have to install any software. That being said, KiCad is free, open source, and runs on all major platforms, so that is what I recommend people use. Firmware tool-wise, it depends on what microcontroller you're using. A lot of them are supported by GCC, so you have open source tools there. MPLab for a lot of microchip devices, it's free from them, but it's proprietary. And then you could also use Arduino if you're familiar with Arduino for some of them, which is pretty cool. And then there's some debugging and flashing tools, and we'll dive a little bit more into those when we get to that part. Hardware tools-wise, you will need a multimeter because you need a way to figure out what's going on your circuits, and a multimeter is an absolute must. You'll need a soldering iron. Even if you're going to have them professionally assembled, at some point you're going to find something you need to change locally, so you'll need a soldering iron, and you'll need some way to program and debug it. And it depends on which microcontroller, but there's this really cool project called Tigard, I hope I'm saying it right, down here that can interface with a bunch of different things. It's all software defined. It's made by a hardware hacker named Joe Fitzpatrick. Full disclosure, it actually came out of a conversation he and I had at a conference. I did a prototype. My prototype was terrible, but he then took it and made it into something that's actually usable for people. So way to go, Joe, for doing that. A logic analyzer or hot air station are nice, but optional. Logic analyzers let you see like data that's going over individual traces on a circuit, and you can see like, oh, this is sending this data, and you can actually see the individual things and decode it, which is pretty cool, but also only necessary if you are having chip-to-chip communication that is digital. And a hot air station is just nice for doing surface mount soldering. So schematic design. If you have a concept, you need to have some way of representing that concept. And in electronics, that's called schematics. If you've never seen a schematic before, it's just a representation of the logical flow and connections of a circuit. And so this is about the simplest possible schematic you can have. On the left-hand side, you have a battery. At the top, you have a resistor. And then on the right-hand side, you have an LED. And so if you put all this together, you'll get an LED that lights up. Nothing fancy, but it's a basic schematic. You draw it in an EDA tool, and you can even have virtual connections. So you don't have to run wires everywhere. So you have connections that will be labeled ground to connect all of the things together. And these are very industry standardized symbols. If you take this schematic and you send it to someone else that knows what schematics are and what the symbols are, they will immediately be able to tell what each of these components are, even without reading the names, and understand what's going on there. So that's the key behind schematics, is it's a way to communicate the logical intent of a circuit. So if you're not familiar at all with electronics, a little bit of basics. If you are, I apologize. These will be like electronics 101 concepts here. Voltage, sometimes you'll hear referred to as potential, is just the difference between charges between two parts in a circuit. So this is how much capability is there for current to flow from one point to another point. So the outlets on the walls here have, depending on who you ask, 110, 115, 120 volts on them, because North America is weird and the standard is kind of hard and ill-defined. DC circuits have a continuous voltage, so it's basically a flat line. AC circuits are what you see here, where it's up and down, which is what you have coming out of your wall. Badgelife basically only deals with DC circuits and DC power supplies. So for the rest of the time, that's all I'll talk about. And the one point on the circuit is arbitrarily chosen and called ground. In not battery-powered electronics, that's usually at the same potential as actually ground that you're standing on. In battery-powered circuits, it doesn't matter. Just by convention, it's the lowest point of potential in the entire circuit. So what is current, right? You hear about people tell you, oh, it's not the volts that kill you, it's the amps that kill you. Well, that's true if you're worried about getting electrocuted. Current is how much electricity is flowing. So voltage, sometimes there's this analogy to plumbing and water, and voltage is the pressure in the pipe. Current is how big is that pipe that all the water is flowing through it at the same time. And so the same thing is true in electronics. Amps, which is what current is measured in, is how many electrons are flowing through a particular circuit at a particular time. Current is something that is pulled, though. Your device demands a certain amount of current, so you can use a power supply that says it's rated for 10 amps and still only pull 1 amp out of it. That's fine. It's not going to try to force the other 9 amps down the throat of the circuit that you're attaching to it. Basic components. We've talked about batteries and power sources. Resistors literally resist the flow of current. They are there to limit the amount of current that flows through a particular section of your circuit. Capacitors basically buffer electrical charge, so they're a device that resists current flowing in and out of them. They're often used on power supplies to stabilize the power supply, because what they will do is act as a reservoir for additional current when the voltage is changing quickly. Diodes are interesting because they only allow current to flow one direction. Some diodes give off photons while they're only allowing current to flow in one direction, and so they produce light, and so we call those light-emitting diodes, which is pretty cool. And LEDs are a requirement of Badgelife, I think, because I've never seen a badge that wasn't absolutely studded with LEDs. There are some relationships between all of these concepts, and a couple of them that you will be helpful to know. You don't have to know them for the rest of the talk, but if you ever get into this, you'll have to look these up again, and they're the relationship between power, which is what's expressed in watts, is just volts times amps. So when you hear something as like, oh, it takes 60 watts, then that's some combination of voltage and current that multiplies to 60 watts. And then the other one is Ohm's law, which is basically defining when you have a voltage and a resistance, how much current will flow through that resistor. This one is actually kind of useful because on LEDs, we want to limit how much current flows through them. And so you need to know how much voltage is going into them to figure out what resistor you will need in there. And we'll talk about that in just a moment. These are some of the more common schematic symbols. They're included here as a reference, not an expectation that you will memorize them all in the next 10 seconds of this slide being on the screen. Voltage regulation is a little bit of a funny thing. Components typically have a certain voltage that they expect to be coming into them. And in modern circuits, that's most often 3.3 volts, 1.8 in low power things, and it gets down even lower below that, but you won't worry about those. You can't just use a resistor to control what voltage you have, because as we discovered with Ohm's law, the voltage drop across a resistor depends on how much current is flowing through it, and your current is not going to be a constant if you're changing the brightness of LEDs or turning them on or off or doing anything that requires processing power. So what we use voltage regulators, and these are basically components that have a feedback loop inside them and control how much voltage you get out of them. On the top, we have a linear regulator. This is what I recommend you use. As you can tell, it is very simple. On the bottom, we have a switching regulator. These are very efficient. They're how you get little power bricks that can do 65 watts for your laptop and things like that. However, as you might be able to tell, they take a lot more to get working correctly, and you will spend a lot of time debugging them. Additionally, there's two concepts you should be familiar with: series and parallel circuits. The names are kind of just what they sound like, but the important thing to know about it is in a series circuit, all of the current flows through the components in series. So your current is the same through each of those components. It is always the same amount of current. The voltage drop will vary depending on the component that is flowing through. In a parallel circuit, they all are exposed to the same amount of potential, but different amounts of currents will flow off of them. So in the series circuit, you think of it as one continuous pipe, and in the parallel one, we have here like two larger pipes and then one smaller pipe that is has more resistance, and so you get different amounts of current flowing through it. So LEDs, we said, you really like LEDs. It turns out, though, that if you just hook up an LED to a power supply, they don't limit their own current. And if you have something that doesn't limit the current flowing through it at all, it's basically like dividing by zero, and infinite current tries to flow through it. And in an LED, that results in the LED glowing very, very brightly for a very, very short period of time, and then it never glows again. You can try this, though. LEDs are super cheap. Hook them up to like a 12-volt power supply. Don't have your fingers on it while you do it, but unless you want little tiny burns from it. Yeah, wear safety goggles. I've actually never had one explode, but yes, do wear safety goggles. I've only had them just burn out internally. Capacitors, on the other hand, do not put those directly across a power supply and turn it on without wearing safety goggles because their failure mechanism is exploding. So typically for most LEDs, 20 milliamps is what you're targeting for garden variety LEDs as a maximum. But modern LEDs are actually really efficient, and you put 5 milliamps through it, and you're still blindingly bright. So you need to play around with it often to figure out what brightness you're targeting. And then you need to calculate your resistance using Ohm's law, right? So here we have one that conveniently I want 2 volts across it at 20 milliamps, and I have a 3-volt power supply, so I need to drop 1 volt at 20 milliamps because they're in series, and that tells me I need a 50 ohm resistor. This is intended just as an example. The way that you really do this is you type LED resistor calculator into Google and tell it what you're going to do. If you're an EE, I'm sorry for simplifying all of your career down to type it into Google. Some quick rules of thumb for a good schematic, though. You want to group things by function. Don't just throw things wherever they fit on the page. All the stuff related to your power supply over here, all your LEDs over here, all the microcontroller stuff in the middle, because again, this is not about how it will actually be laid out on the physical finished thing. This is about expressing a concept and making it easy to understand, right? So imagine if you're reading a book and the author goes, well, he put together a power supply and then connected a microcontroller and then added some LEDs and then put some capacitors for the power supply and then put some resistors for the LEDs and then connected some things to the microcontroller. You don't want to follow it that way. So think about it in terms of like you're telling a story. Here's how I regulate the power. Here's how I have my logic. Here's how I have my LEDs for output, right? And I'm simplifying to assume that you're just getting LEDs for output, but whatever else you might have, group it by what it's doing. It will make a lot more sense when you go back to it after taking a month off from it. Positive voltage at the top, ground at the bottom, and generally speaking, current in on the left, current out on the right, so that you can kind of follow the flow through everything. And again, this is just to make it easier on you. And you can use things called named nets instead of dragging a wire all the way across the sheet. So it's pretty common to have like a named net that's like called 3V for your 3-volt power supply instead of having wires that run everywhere and you have to follow them on the chart. Coin cells are like 30 cents a piece. At some point, you'll put together an early prototype. This is an early prototype of one of my badges. It's on a breadboard. The big blue thing is actually a development board by the microcontroller vendor. That's nice to have because you know that those work, because people who actually do have a degree in electrical engineering put that together. So at least something on there works. In this particular case, I was actually able to make the words hacked, or the word hack display on the display here. The red box there is actually a logic analyzer because I'm examining the data that is being sent from the microcontroller to the display driver. If I have the logic analyzer out, that means something didn't work the first time, because usually I'm just a hook it up and see what happens kind of guy. That being said, you'll go through a couple of iterations like this where you have little wires all over the place. Hopefully you don't have a cat that likes to play with wires. I do, which makes these kind of projects interesting, and whenever I put it away for even a short period of time, it needs to go into a box, not left on the desk. But it's super useful if you have breakout boards for components. Like the display down there is actually a breakout board from a company called Adafruit in New York. And then again, the big one is from the vendor of the microcontroller. So I was able to do a quick proof of concept using those as I was testing my schematic. Firmware. I've said the word firmware before. If you were here yesterday, you heard some people talk about firmware in various embedded in IoT contexts. Firmware is just like embedded software. It's software that sits on the microcontroller and it does a thing. If you're going to have a microcontroller, you're going to need firmware, because otherwise it just sits there and reset and doesn't do anything, and it's not a very interesting badge project. The cool thing about firmware is that you can go back and fix a lot of your mistakes later. I come from a software background mostly, where it's lovely to be able to hit like compile and then test and then compile and then test and go through that iteration like 20 times in a day. If you're doing that on your circuit board side, you're doing like fix the circuit board, send it to the fab, wait a week for the shipment to come back, and that development cycle is a lot slower. So try to fix your problems in firmware instead of in hardware. You do need to flash it to the microcontroller, so it's not quite as quick as doing purely software things, but it's still easy to iterate with it. And then this here is just some basically some timer-related firmware where you set a bunch of bits, and the exact meaning of the bits depends on the microcontroller you're using, but the data sheet tends to tell you what you need. Some of the challenges with firmware, well, you do have to flash it again to iterate it. There's no operating system. You can't just open a file and read from it. You have to manage all of that yourself. There's no threading or process scheduling, so you have to figure out how to do things asynchronously if you have timers and things like that. But the good news is usually you can just get an interrupt, which means that the hardware will magically jump to a particular place in your code for you at a certain it becomes very difficult to debug. And depending on the microcontroller you're using, documentation may be variable. For example, the ESP32 is a really well-known Bluetooth and Wi-Fi microcontroller. Espressif's documentation is okay, but the community documentation is really, really good. You can find people have done anything you can imagine with an ESP32. On the other hand, if you use an Atmel SAMD51, there's not that much community documentation, but the company actually made pretty good documentation for it. And then if you use an MSP430, good luck. So how do you control pins, right? Like you have a microcontroller and it has these little pins, and theoretically you want to do electrical things with the pins. Usually you actually have to do two steps, because the first thing you have to do is tell it that I want to use this pin as an input or an output. And so you tell it I want to use it as an output. And then you have to tell it, okay, I want it to like have voltage present or not have voltage present. And we refer to that as being high or being low. So when you take a pin high, there is voltage coming out of there. And then when you take it low, there's not voltage present. And when a pin is in an input state, you can read from the pin and find out whether it's high or low sort of state. So that you can use that for like buttons or other user interface elements of a badge. Your microcontroller will have some peripherals. Almost all microcontrollers, unless you're buying the absolute cheapest thing you can find, have at least timers, which is great if you want to do anything at some sort of interval. And like I said, that calls an interrupt handler, but just basically a chunk of code that you can do something with at a interval. Some of them have hardware PWM, which is just a fancy way of saying it will turn one of the pins on and off really fast for you. Without you having to do it in code, which is nice if you want a variable brightness of an LED. So you don't actually vary LED brightness by changing the amount of current that flows through it. The way most LEDs brightness is varied is just by turning them on and off at really fast rates in varying